Let us now consider subsets of the real number system. So we will usually denote the set of real numbers by this Blackboard font. So this is how we'll denote the set of real numbers. Like I said, because the set of real numbers is not countable, we usually will use a number. You can use a number line, and then you have the 0 in the middle, and then these are the positive numbers, and these are the negative numbers. Now, we will usually consider the following subsets of R. The first one is a set of natural numbers. So N here is a set of what we call natural or counting numbers. So they start with 1, and then you have 2, and then you have 3, and so on. So N, unlike R, even though it's still infinite, it is countable, because what you now do is that you're starting from here. This is 1, and then you have 2, and then you have 3, and so on. Then we will consider the set of integers. So the set of integers, like we saw, are positive or negative whole numbers. So numbers that are integral. So 0, 1, 2, 3, and so on. And then -1, -2, -3, and so on. So they stretch forth in both directions. So here you would have the negatives, and so on. But we also have other kinds. We have, for instance, a set of rational numbers. So rational numbers are numbers that can be expressed as fractions. So you got A over B, where B is not 0. So all numbers that can be expressed as fractions are rational numbers. For instance, integers are rational numbers. So if Z is an integer, we see that Z can be written as Z over 1. So Z is also a rational number. So all integers are rational numbers. But there are real numbers that are not rational numbers. An example is the number pi. Pi is not a rational number. I know sometimes in some of your work, we approximate it by the fraction 22/7. But pi is not 22/7. It's close to it, but it is not it. Pi is irrational. It cannot be written as a fraction. Another one is also the transcendental number E. E is also not rational. E cannot be written as a fraction. So we actually do have a nice inclusion. We have N properly contained in Z, properly contained in Q, properly contained in R. And then we can add one more where we consider complex numbers. So complex numbers are numbers that can be written in terms with the real part. This is the real part. And then this part is the imaginary part. And the I there is a number that satisfies the equation that when you take it square, it equals -1. So we've got these sets that we will be dealing with throughout our mathematical journey, and we will see them coming up in most cases. In some books, they represent the set of real numbers with a bold R, but this is fine. So we will defer this example for class. So if you start thinking about these, what will be the members of the following sets? The kind of things you should ask is, can you list all of them? For instance, this one. Can we list all of them? So can we list all the elements of this set? How about this one? How about this one? What are the members? This one in particular should be interesting. We're looking for all real numbers that satisfy this equation. And one of the things to think about, and we'll talk about this in class, is what do the solutions, this solution and this one, look like? Like I said on Monday, it's always good to graph some of these to see how they look like. Okay. And sometimes when a set has no members, we call that the empty set or the null set. And we can denote it by a pair of braces that enclose nothing, or this symbol here. So you've got an O with a cross out of it. So that is called the empty set. So again, we will defer this for class. So these are the sort of examples that we want to talk about. So you realize that all the operations are in there. We've covered the operations of union, intersection, set minus, symmetric difference, and then we took our subsets and complements. Now, one of the things that we may try to do, like for instance, with a universal set like this, is to use diagrams. So if we consider this as our universal set, we would have a diagram like this with our U, and then I would have my A, my B, and my C in such a thing. These sorts of things are called Venn diagrams, and that's what we'll discuss next. So it helps us to give a pictorial representation of sets. And so we will use Venn diagrams. And they are also useful for constructing logical arguments to check, for instance, if an argument is valid or invalid arguments. You may use a Venn diagram. So in the Venn diagram, what we do is that we're going to represent the universal set, the rectangle, and every other set is either a circle or an oval, and then the elements with a period, with then the letter after it to show that it is in that set. So these are examples. So you could have a Venn diagram. You've got your universal set and you've got two sets in there. You will notice, for instance, that we could label the areas. So if we decide to label the areas 1, 2, 3, and 4, we can describe things like, for instance, the area 3 is precisely A intersect B. And then the areas 2, 3, and 4 is the union. And you realize that 1 is the complement of A union B. And so, and you see that 2 plus 4 is a symmetric difference of A and B. And we do the same thing here too. So you got a 1 on the outside. Sometimes in some books, they start with the counting this one in here. So let's say 1, 2, 3, 4. Then you could do 5, 6, 7, and 8. And we can describe the operations on the sets A, B, and C by the unions of the areas that you have. And so this is an illustration of A union B. And once you see what A union B is, you realize that in the previous diagram, that's what I had here. So A union B would be all of this. For A intersect B, it's just the middle part because we want the elements to lie in both A and B. And so we're going to look at this as well. So we'll discuss this in class. So you could try the examples before. So we'll have a universal set. So for these two set problems, we will discuss, you draw a Venn diagram, and then we would see which areas are A union B complement, A intersect B complement, A complement union B complement, A complement intersect B complement. And the question to ask is, what are the relations between numbers 1, 2, 3, and 4. And then we will check 5, 6, and 7 as well. So going forward, we will revisit sets again by now looking at, once we have the tools of logic, how can we establish more relations between sets? Now we know what the tools of logic, it becomes easier to establish some relations like equality or subsets or certain kinds of proofs. So this is the first part of set theory. We will revisit set theory again in the next couple of weeks.